So I would like to make several statements regarding results we obtained last time. If you remember, we consider neutrino mixing in oscillations in a magnetic field which has a longitudinal and transversal component in respect to neutrino propagation. And we derived an effective Hamiltonian of evolution accounting for matter and also accounting for two possible spin orientations of the mass states. Yeah? And I would like to write the consequence for the most simple case that vividly exhibit the role of longitudinal and transversal magnetic field components on generation of neutrino mixing and oscillation, specific oscillations. So let's first consider, this is like an addition to what we discussed last time, but today is 18th of March. Yeah, okay. So we just add a short discussion. So let's consider neutrino evolution between two neutrino states of equal masses and different helicities. So evolution between neutrino mass, let's say 1, and helicity given by this number +1, and neutrino of different mass 2, and helicity opposite. So this is in a magnetic field, yeah? In a magnetic field. So we, from the general expression we derived for neutrino component wave function that describes two possible masses and two possible helicities, I just extract only a part, 2 by 2 matrix, this evolution Hamiltonian, that is a part of this 4 by 4 Hamiltonian. And I will write, I will write excuse me, I would like to see first when the mass is equal. So the most simple way. So the corresponding evolution equation for these particular transitions has the following form: nu of mass s equal to 1, nu of the same mass s equal to -1. And we obtained from the previous lectures that this is the magnetic moment of neutrino, 1, 1, it is diagonal magnetic moment, as we call it, divided by 2. And here is 2 by 2 evolution matrix, the longitudinal part of the magnetic field, suppressed by the gamma factor, then the transversal magnetic field, and again the same minus longitudinal part divided by gamma on the same vector. 1, s equal to 1, nu 1, s equal to -1. So this is the magnetic moment of neutrino of mass 1, and this is gamma. This is a gamma factor. That is the energy of neutrino divided by the mass of neutrino. Yeah. So we see that mixing between different. This is of course not longitudinal, but 1, 1, yeah, magnetic moment, yeah? And here is let's distinguish this. So the mixing is due to interaction of magnetic moment to transversal magnetic field and interaction of these mass states of neutrinos through magnetic moment coupling to the longitudinal part shifts the energy of neutrinos. Yeah? Okay. Another case, when we consider again transition of spin orientation, and also we see now the case of two different masses. So we consider neutrino 1 of mass 1 with the fixed spin orientation and transition oscillations under the influence of transversal and longitudinal magnetic fields to the mass state 2 with the opposite spin orientation. So in this case, the expression that we can derive from our more complete 4x4 Hamiltonian will be a little bit more complicated because we should add here in the diagonal the term that describes difference of masses. Yeah? So, again, I, D, T, neutrino 1, S equal 1, neutrino 2, S equal minus 1, equals to, and here this is Hamiltonian, again 1/2, I just put after, delta M squared divided by 4 energies of neutrinos. We suppose that the energies are equal. This is a kind of compromise. So they have different masses, equal more or less energies, and equal momenta. Because the mass contribution is very, very small. Everything is, we deal with the relativistic neutrinos. So plus magnetic moment of the first neutrino mass state multiplied by the longitudinal magnetic component divided by gamma 1. Then the second term in the first line, this is transition magnetic moment that coupled neutrinos with different masses, and interaction of this magnetic moment with the transversal magnetic field produce the mixing between different mass states with different spin orientation of neutrinos. Yeah? This is transition magnetic moment. Yeah? And here again, the same, mu 1, 2, multiplied by the transversal magnetic field, minus delta M squared divided by 4 energies of neutrino, minus magnetic moment of the second neutrino multiplied by the longitudinal magnetic field divided by gamma 2. Gamma 2 is the Lorentz factor for, this is from another formula. Yeah? The gamma 2 is the Lorentz factor for neutrino with the mass 2. So we see that if we compare these two cases, the mass square difference is added because it corresponds to the difference of energies of two neutrinos and with the same momenta, yeah? Mass square difference. So the mass square difference, and 1/2 I should put here, yeah? And also I should put here, for completeness, correctness, nu 2, S equal minus 1. Okay, yeah? And the third And the third case, when the mass is changing, but the spin orientation is not changing. I put plus. The third case, when we consider mixing and transitions between different mass states with equal spin orientations, for instance, S equal to 1 plus 1, the second mass neutrino state with the same spin orientation, also in the magnetic field. Then we have the following. I d over dt, our state, 1, S equal to 1, newt mass 2, S again 1. And here is the Hamiltonian. Let's put, don't forget, 1/2. Again, mass square difference divided by 4 neutrino energies, plus magnetic moment of the first neutrino, mu11, we just indicated, multiplied by the longitudinal component of the field divided by gamma factor of the first neutrino. Then the transition magnetic moment, neutrino 1, 2, multiplied by longitudinal component of the field, longitudinal component of the field, and here is gamma 1, 2 equals to 1/2 gamma 1 minus 1 plus gamma 2 minus 1. So what is very important here, is like a new phenomenon, I should say. Then the same in the second line, magnetic moment transition 1, 2, multiplied by the longitudinal component of the field divided by this gamma 1, 2. And here is minus mass square difference divided by 4 energy of neutrino plus magnetic moment of the second neutrino, longitudinal field, multiplied by gamma 1, 2. So we see that in general, a mixing between two different mass states with the same spin orientation appears in case when the transition magnetic moment is not zero, and also due to longitudinal magnetic field. So not only transversal magnetic field generate an addition mixing between different neutrino species, but also longitudinal. It's a little bit surprising, because just naively it was expected that the longitudinal magnetic field coupled to magnetic moment shift the energy, put addition terms in the diagonal of the evolution Hamiltonian. But here is an additional mixing. And you understand when we, from this basis, if you go to the flavor basis, the same situation will be realized also for the flavor neutrino mixing oscillations. And also, there will be additional mixing in the flavor basis, addition to mixing that is governed by the mixing angle, initially come from the nature, I should say. But this is the generated additional mixing between electron muon neutrinos in the flavor basis due to not trivial, if not zero, transition magnetic moment in the flavor basis. But we have all these formulas. I don't want to repeat. And probably in one of the next our lectures, I will just write the final solution for the same phenomena, but in the flavor basis. And we shall discuss how it can be visualized, and probably here I should put again the final equal to 1, nu s equal to 1. Yeah? Now this is like notes that I would like to add to our previous lecture. So, now I would like to discuss today a slightly simplified version of this mixing and oscillation phenomena of neutrinos due to magnetic moment interaction with the external electromagnetic field, and we shall manage to go to the very end and derive an exact formulas for oscillation probabilities. So consider neutrino mixing and oscillation in a constant magnetic twisting field with a twist. So in the constant twisting magnetic field, what it is? This is a field that is constant and perpendicular to, in respect to neutrino propagation, and the effect of twisting is a rotation in space. Be transversal, constant, how to write, no, it's better to write like this. The field is modulus of this constant component multiplied by exponent with phi that is a function of time. This is a constant in space, in time field, but it rotates in space, but constant in time, yeah? But it rotates along the neutrino propagation. This, why these fields come into the market? So because in some models of the structure of the electromagnetic field, and particular magnetic field in the sun, it looks like the following. There are some small regions with constant arbitrary orientated magnetic field, but when a relativistic neutrino is propagating, it's like a domain structure. In the reference frames related to relativistic neutrinos, it seems like the rotating, twisting magnetic field. And sometimes it is used to mimic the astrophysical magnetic fields. And I would like to say that this provides a kind of approach of another new phenomenon that was proposed and investigated in my papers about maybe 20 years ago. This was known, and once I just discussed this and study by papers of other people, I just get a feeling that probably it will be possible to solve the same problem, not in a constant magnetic field, but in the electromagnetic field of an electromagnetic wave, because it looks like a stopped wave, yeah? So, and finally, in out 2 or 3 papers with my students at the time, published about 20 years ago. And also people will get the diplomas and PhD dissertations. We were the first who just stated this problem, neutrino mixing and oscillations, in the field of electromagnetic wave. Nobody discussed this before. And then we go further and investigate some other very interesting phenomena related to neutrino spin evolution in external environments, including simultaneous presence of electromagnetic fields and matter that can be at rest or moving with a high speed, with relativistic speed. So it's a very complicated environmental situation, but we solve it starting with this particular very simple and quite easily accessible for an exact calculations on the blackboard here. So this is a twisting magnetic field. So we can write that this is, again, this is the field, but with the 2 components. Let's fix the reference frame like this. Let it be x, and this is neutrino momentum along x. This is y unit vector. This is k. This is j, and the field it is a superposition of k b 3 plus j b2, something like this, yeah? These unit vectors. Okay. And we consider also the external field, and we consider neutrino state as follows. Also, we deal with 2 flavor neutrinos with opposite helicities or chiralities, because for relativistic neutrinos, you know, helicity is nearly chirality and vice versa. Yeah? So we use the following neutrino state for definiteness: electron left neutrino and muon right neutrino. So we shall derive evolution equation and solve it for this particular neutrino state. Yeah? So, and also we with magnetic moments. M, I, J with different indices that contains mu 1, 1. We just use a simpler notation. This is magnetic moment of the neutrino of mass 1. Yeah. Then magnetic moment of the second neutrino. This is mu 2. And magnetic moment of mu 1, 2 to 1. This is at the transition magnetic moments. So we shall account for all possible types of magnetic moments introduced in the mass states, as we did last time. But if you remember, we also derived an effective magnetic moments for the flavor neutrinos that contains these initial fundamental magnetic moments introduced for the mass states of neutrinos, but then through mixing, we also can determine the effective magnetic moments for electron and muon neutrinos, and also the transition magnetic moments in the flavor basis, you remember. This depends on these fundamental values, yeah? And also depends on the cosine and sine of mixing angle, you remember, yeah? Okay, so this is the result, this transition is a result of transition from the mass state basis to the flavor state basis. Yeah, we write the Hamiltonians we discussed with you just a moment ago, then multiply by left and right by u cross, and apply this procedure to the magnetic moment interaction with magnetic field in the mass basis, and derive the corresponding expression for the magnetic moments, effective magnetic moments for the flavor neutrinos, electron, muon, and transition in the flavor basis magnetic moment of neutrinos. Okay? Well, so we account for mixing of neutrinos. I discussed with you mixing. So we suppose that electron neutrino is neutrino 1 cosine mixing angle plus neutrino 2 sine mixing angle theta. Neutrino muon neutrino is minus neutrino 1 cosine theta sine theta plus nu 2 cosine theta. So we introduce mixing, and now we consider, we consider the problem of evolution. Okay? The problem of evolution. The problem of evolution of this state, and in particular, we are interested in transitions between different mass flavor states in twisting magnetic field plus matter effect. So this is what we are discussing now. And the solution should be found for the following evolution equation. I, d over dt, our neutrino state, electron left, muon right. And here we have two contributions to effective Hamiltonian. One is, as we indicated, H wave plus the Hamiltonian of magnetic moment interaction with external magnetic field in the flavor basis. Because we are working now in the flavor basis, yeah? Last time we derived this guy exactly for the flavor basis. I don't want to repeat it, I just only use part of that 4x4 matrix that correspond to our particular problem of evolution or communication or transitions and oscillation between two flavor neutrinos. Yeah? But we have a complete set of all elements of this effective Hamiltonian that have 4 lines and 4 columns, yeah? 4x4 matrix. So where? Yeah? I am just writing what it is exactly, because even I sometimes used to forget this, but I just spend 5 minutes to reproduce all formulas. Today I just write it because to have it behind the eyes. Yeah, where this Hamiltonian is composed of the vacuum evolution Hamiltonian. Prime means after transition to the flavor basis. Yeah, because in the mass basis, Hamiltonian is very simple. It's a diagonal. Energy stands on the diagonal with zeros of diagonal terms. Yeah, okay. But again, accounting for mixing may transition from mass basis to flavor basis. We multiply this very initial Hamiltonian to U and U cross, and we obtain this Hamiltonian. Yeah, plus Hamiltonian that have been introduced exactly in flavor basis, because we use it, we calculate the addition to the Hamiltonian by averaging the Lagrangian of weak interactions of our neutrinos, electron and mu neutrinos in our case, with particles on the environment. Also we have to fix in order to determine exactly what it means. We fix the matter composition. Again, we use the normal matter composed of electrons, protons, and neutrons with equal number of electrons and protons. So, and this part was calculated for the flavor, particularly for this problem, for the flavor neutrinos. Yeah. So we suppose matter. Matter. We suppose that there are electrons and protons and also neutrons. So this is a particle number density, electron number density, this is proton number density, and this is a neutron number density. Also, we suppose that there are no electric currents, so in general, matter should be electrically neutral, so number of electrons per cubic centimeter should be equal to, more or less, equal to the number of protons. A normal stable matter without currents. Yeah? So recall, I just so initially in the physical basis or in the mass basis, we have this. This is mass basis. Or physical basis for the mass states of neutrinos. Yeah. This Hamiltonian we introduce or fix or derive as you wish. This is just an energy of particular neutrino. And we use the relativistic approximation, and we just write that this is the energy that is equal to both mass states m alpha squared divided by 2 momentos of neutrino plus. So we use only these first two terms here, yeah, in expansion. Okay, and I just put, okay. So, where, once again, where this Hamiltonian can be written in the following form. This is not important part that is proportional to the unit matrix, and it can be easy, just forgotten, but for completeness I write it. This is unit matrix, it's not important when you calculate the probability of oscillations. Mass square difference, delta m squared, divided by 4 energies, or models of momentum, 1, 0, 0, minus 1. This is mass square difference, a very important mass of the second neutrino minus square root of the first neutrino, mass square difference. So, in case of mixing, between different mass states and flavor states, we have flavor neutrinos superposition of the mass states, and in the case of two neutrinos, it can be parameterized by only one angle, cosine minus sine, cosine. This is mixing matrix, and for evolution of the flavor states, I just put here x, because for relativistic neutrinos we can use this transition, evolution in space, and equal to evolution in time for relativistic neutrinos. So this neutrino flavor, U, H, U cross, and this we call prime, Hamiltonian prime vacuum, yeah? Okay. We introduce matter. So there are two contributions, neutral current and charge current contributions. So neutral current contributions can be described like this. It is electron neutrino, and this is electron neutrino. It is dead boson, and here are all particles on the environment: protons, neutrons, electrons. Neutrons, protons, electrons. So of course we are not interested in the quark structure of nuclei, yeah? And charge current, mediated by charge boson, neutrino electron left, neutrino electron left, neutrino electron. I just should write like this. This electron, this is neutrino electron left. Yeah. So in our case, we have electron left neutrino that does interact with the environment through neutral and charge currents, and also another state is the right-handed muon neutrino. And the right-handed, due to the structure of electroweak Lagrangian that describes interaction of particles, in particular with these bosons, they are, in the case of massless neutrinos, they are sterile. But if the mass is very small in respect to energy, it's nearly sterile. So we suppose that muon neutrino is a sterile particle. So it means that none of these contributions appears in the potential of the muon right-handed neutrino. So we are considering mixing and oscillations between electron effective neutrino coupled with particles of environment and sterile neutrino. So it means that for this guy, all these contributions are zero. So this is a quite different situation in respect to what we discussed when we considered the mixing and oscillations between flavor neutrinos without change of spin orientation. Because we, at that time, we considered muon neutrino also as an active neutrino that coupled with particles differently in respect to electron neutrino coupling, but still it interacts with the environment, yeah? Well, but now we have to adjust the potentials. We cannot use the exact potentials that we used before for the flavor neutrino mixing and oscillations. So, and just to sum up what I have discussed, we can write that the effective matter potential for the electron left neutrino due to neutral current interaction is 1 divided by square root of 2 Fermi coupling constant, the number of neutrons. Because protons and neutrons have opposite charges and contributions kill each other. Only contribution from the coupling of effective flavor neutrino, in our case the electron neutrino, survives on neutrons. Yeah? This is the neutral. For another guy, in the flavor mixing and oscillations, have the same contribution, yeah? But now that is zero. And again, for electron neutrino left, charge current is like it was. This is square root of 2 G Fermi, the number of electrons. So potentials, the potential for muon right-handed neutrino is zero. So it's a sterile neutrino. It's zero for neutral currents and also from charge currents, because it's sterile neutrino, okay? Then, this is the difference in respect to what we have already discussed. So, and then we can write the difference of potentials that matters and that is important for neutrino oscillation probability calculations left to muon neutrino right, the difference of potentials. In case when matter is electrically neutral, is equal to square root of 2 Fermi constant and E minus number of neutrons divided by 2. This is addition part in respect to what we have derived when we considered neutrino mixing and oscillations between electron and muon neutrinos. Because for electron and muon neutrinos, these parts are identical. And in the difference of potential energy, it cancels out. So it was like this. And normally, in many papers and textbooks, when people consider flavor neutrino mixing and oscillation in normal matter, they show only one diagram, scattering of electron neutrino on electrons. The rest contributions cancel out for different reasons. I don't want to repeat. Yeah? Okay. That is the difference. Okay. Thus, if we sum up all we have discussed, we can write the effective evolution equation for the considered neutrino state that can be muon right-handed and electron left-handed. The effective Hamiltonian can be written in the form, this is the energy, the energy of left-handed neutrinos. This is the magnetic moment, effective magnetic moment in the flavor basis. We have calculated last time. This guy, yeah? This is a combination of initial fundamental magnetic moments introduced for the mass states. Please see your notes from previous lecture. And here is magnetic field multiplied by this factor that accounts for twist of the field. Phi depends on T. This is magnetic moment, transition magnetic moment. And this is the energy of this neutrino. This is the starting point, nu E L, nu mu L. Okay? Now we can go further and write explicitly, accounting for what we have already have written today. So we just write in the following way. This is something that is not important, but still I will just, for completeness, write it, because this part is proportional to the unit matrix, m1 squared plus m2 squared, divided by 4 momentum of neutrinos, multiplied by the unit matrix. And here I explicitly write 2 by 2 matrix, and then we operate with this part of the Hamiltonian. Minus mass square difference, delta m squared, divided by 4. I just, instead of modulus of momentum, I will write the energy. Yeah? For P0 cosine double mixing angle theta. I just reproduced results that we have obtained in the previous lecture. Now, I included these results. Yeah? Plus the potential of electron left neutrino, then magnetic moment in the flavor basis. Indeed, this is transition magnetic moment, because we consider transition between different flavor states. Yeah? Also, in this term, there are transition magnetic moments in the mass basis and of diagonal magnetic moments, and diagonal magnetic moments for the mass states of neutrino mass 1 and 2, multiplied by the specific combinations of cosine theta and sine theta. Yeah. Minus I phi. Then the second line, magnetic moment of the same type, multiplied by the magnetic field, exponent I phi, delta m squared divided by 4 energy of neutrino, cosine double theta. Yeah? And everything should couple to our neutrino state, that is electron left and muon right neutrino. What is important, only electron left coupled to particles of environment, and the right-handed mu neutrino is sterile. That's why here is nothing. Yeah. Now, our goal is to find a solution. In a similar way, we did, and we solved this problem for the case of flavor mixing and oscillations. The only problem here is this term, because phi depends on t. There is a need to think about and to do something. And there is a very nice approach how to treat this twisting effect of magnetic field. And just in a moment I will show that the problem can be reformulated in a such way by transition, by unitary transformation from this basis to another one related by unitary matrix, and for which in the new basis this term will disappear here and addition potential will appear here. And as soon as two bases I am discussing are related by unitary transformation, the solution for the oscillation problem, the probability, will be the same. So we shall just, after transition to another basis, we just move this phi to the effective potential, really. The same will happen, I just announced that very similar approach can be used when was used when we consider the neutrino mixing and oscillation in the electromagnetic field of electromagnetic wave. Yeah? And in that case, we have here also the omega appears. Yeah, this phi, the phi over dt is the omega. Yeah, and in that case, an addition appears here. This is proportional to this omega. A very similar formally. Yeah. So let's do what I have just announced. Consider a new basis. So we just, from our basis to new basis, prime. So it is a transition to a rotating system with the same characteristics as the rotation of the constant magnetic field, transversal magnetic field. This is governed by this same angle phi. So what I mean, we just introduce new basis. I think that you will not, you will distinguish this mixing and this transformation. Yeah, this is, I just show exactly what it is. To new basis, where U now, yeah, is nothing but 1 exponent minus I phi divided by 2, 0, 0, exponent phi divided by 2. So this is a transition to another basis. This is unitary matrix, unitary transformation, and it is possible to show that the solution and the problem of mixing and oscillation, the solution, the probability will be the same as in this basis and as in this basis. And now let's make this transformation and let's consider evolution now, reformulate evolution in terms of new introduced basis is indicated by prime. Yeah? So what we have? New evolution equation for this prime, yeah, neutrino state. I just put very accurately I divided by 2, exponent with minus phi divided by 2, 0, 0, exponent I phi divided by 2. Multiply by the derivative of the phi. I just put this, put in the equation, yeah? And calculate the derivative, d over dt, yeah? Accounting for dependence of phi on t. So this extra term appears here. So nu prime plus exponent minus I phi divided by 2, 0, 0, exponent I phi divided by 2, d over dt, nu prime, yeah, equals to h prime, a wave, yeah, and now I just introduce this matrix and u and the field in new basis. Here is the a new evolution equation for neutrinos in new basis that is related to the initial one by this unitary transformation. And phi is the same as in expression for evolution in space of the strength of a constant magnetic field, transversal in respect to neutrino propagation. Yeah? So let's introduce another matrix. Let's introduce this. We just call it U prime, a new matrix. So this, yeah, okay. This is U. And what we also need, the Hermitian adjoint matrix, U cross Hermitian adjoint, сопряженный, да? Conjugated as a wish. Yeah? Is nothing by E I phi divided by 2, 0, 0, E minus phi divided by 2. Okay. I just introduced all the needed matrices, and now let's make very simple manipulations. Let's multiply this evolution equation by U. What to? Yes. Okay. Multiply by touch? No? Oh, okay. Multiply by U cross here from the left side, yeah? So, and we get, after this multiplication, we get I d over dt nu prime, and here is the new Hamiltonian of evolution for neutrinos in the new basis. u cross h wave u plus phi dot, the derivative of time, divided by 2, u cross u prime neutrino prime. This is what we get. This is important, this phi. So you see, this guy is one, is the unit matrix, yeah? Obviously. So, and we see really, after this transformation, unitary transformation, this phi enters as phi derivative of time of 5, and this looks like an addition to effective Hamiltonian. So the effective energy is changing, yeah? And now we can solve this problem. Now we can solve this problem. So, as I mentioned, this is, this is u equals to minus 1, 0, 1. It's like this, yeah? So, and now we have to calculate this to go further. Let's do this. Can I move? Thank you. So let's calculate u cross h wave u. Let's write explicitly what we have. Exponent I phi divided by 2, 0, 0. Exponent minus phi divided by 2. Then I just introduce A mu magnetic field, exponent minus I phi, mu magnetic field, exponent plus I phi, and C. I just reproduce the structure of this H wave, yeah? This is magnetic moment E mu, A and C, the corresponding terms, yeah? That doesn't depend on phi. Yeah? And here we put U. So if you just multiply these guys, we get A exponent phi divided by 2. Magnetic moment, transition magnetic moment, I just miss the indices here for make it shorter. Magnetic field minus I phi divided by 2. Magnetic moment, the same. Magnetic field I phi divided by 2. And C, exponent minus phi divided by 2. Yeah? And let's now explicitly write U matrix. This is 0, 0. Exponent I phi divided by 2. Exponent minus I phi divided by 2. Just very simple result. A mu E mu B, I restore. Mu E, the indices B, C. So, it's very interesting. It is the same with very, very simple result. So thanks to this quite tricky transformation, we simplified the effective Hamiltonian. So just we can conclude that rotation of a magnetic field strength in space acts in oscillation phenomena as a potential that is proportional to the derivative of this phi. Yeah? So, and again, the same will happen when one consider neutrino mixing and oscillations in the field of electromagnetic wave. Phi dot will be equal to omega, the frequency of the wave. Very, very interesting. So just looking for solution for this particular case we are discussing, we get this idea to consider the problem, and we believed that it can be solved exactly. Once again, as soon as transformation between initial neutrino basis to the neutrino basis prime corresponds to a transition to a rotating reference frame that is also parameterized by this angle 5, and the relation between these two bases are given by unitary matrix. The above transformation does not change the probability of neutrino oscillations. So therefore, this is a particular point, we keep the same indication for the neutrino fields. Understand, yeah? So finally we get that I dot neutrino electron left, neutrino muon right, and here it is effective Hamiltonian minus mass codifferent divided by 4 neutrino energies cosine double theta plus potential of electron left neutrino divided by 2 minus phi dot divided by 2. This is an addition to the potential of neutrino. Yeah? Here is the effective magnetic moment in the flavor basis multiplied by the strength of magnetic field, the same. And here, mass square difference divided by 4 energies, cosine double theta minus potential of electron left neutrino divided by 2 plus phi dot divided by 2, and here again electron left, neutrino muon right. Probably you understand that initially we have only here the potential, yeah, but I distributed between this line and this line. You understand that from the point of view discussion of probability of oscillations, you can add or extract to the Hamiltonian evolution any new part that is proportional to the unit matrix. I did this, and now we have half a potential here, and here is minus half a potential. Initially there was 0 here, but this was double without 2 in denominator. I make it to make it more symmetric. More symmetric, yeah? So, now we can rewrite. We shall do the same procedure that was done when we solved the problem of neutrino mixing and oscillation and calculated the probability of flavor oscillations last year. Yeah. So we can write the following equation for which we know how to write the final solution. We introduce sigma matrices minus delta AR divided by 4 neutrino energy, sigma 3 plus the effective magnetic moment in flavor basis multiplied by the strength of magnetic field, neutrino sigma 1 I just recall that sigma 1 is off diagonal and sigma 3 is diagonal with the sum minus. Okay? Where delta LR equals to, we introduce this notation, mass square difference divided by 1, because I just put here 4 energies, cosine double theta minus 2 energy of neutrino, potential of electron left neutrino plus 2 energy multiplied by phi. This is delta. So in addition to real potential, we get an additional part, a mimic potential, due to effect of rotation of the transversal constant magnetic field in space. It's stationary in time, but from point to point, the vector is changing its orientation, and this change is governed by this angle phi that depends probably on time, yeah? Okay? Because neutrino is propagating. So,
delta m squared divided
by 1. I just let's because I already put here the energy in the denominator. Okay, so we are very, very really close to the final solution, and probably we shall stop here. And maybe I will ask you to find the probability. As a function of distance.
As homework?
Sorry?
As homework?
Yeah,
Okay.
because I would like to ask you something to do. And then I will help you next time. And also we shall discuss some particular cases and some relation between, this is a spin flavor oscillations. Flavor is changing and spin is also changing, yeah? This is probability of spin flavor oscillation. in magnetic field. In twisting magnetic field, yeah? Okay. Well, thank you.